Beneath your feet, the ground is moving. Not quickly enough to feel, but constantly, endlessly, grain by grain. Mountains are rising. Continents are drifting. Deep below, the Earth's molten heart churns with heat older than life itself. You stand upon a thin, fragile crust, floating on a sea of liquid rock that has been flowing for over 4 billion years. Tonight we journey into the quiet depths of geology. There is no test waiting at the end. No rush, no urgency. Just the slow unfolding of the planet's most ancient secrets to carry you gently towards sleep. We will explore how mountains rise and crumble, how crystals grow in hidden caves, how the continents wander like slow ships across an ocean of stone, all of it waiting to be whispered into the stillness. Tonight, let's drift off together while exploring over 100 soothing facts about geology. There's no rush here, no test at the end, just soft words and quiet wonders to carry you into rest. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the ancient forces that shape our world. Either way, this space is for you. There is something deeply calming about contemplating the slow rhythms of the earth. Every mountain, every grain of sand, every crystal hidden in darkness carries within it a story billions of years in the making. You are part of that story. The atoms in your bones were forged in ancient stars and delivered to this planet by meteorites. The ground beneath you has journeyed across the globe, carrying continents and oceans through eons of transformation. So settle in. Let your breathing slow, and let the weight of the day drift away like sediment settling softly to the ocean floor. Geology is the study of time written in stone. It tells us how the Earth formed, how it changes, and how it will continue to transform long after we are gone. The planet beneath us is not static. It breathes. It shifts. It remembers. Tonight, we will wander through this magnificent history. We will meet forces that move mountains and powers that split continents. And we will discover truths about the Earth that may surprise even the most curious minds. But there is no hurry. The Earth has been changing for billions of years. It can wait a little longer while you rest. Let us begin with the very ground beneath our feet. Earth's crust is thinner than apple skin relative to its size. If you could shrink our planet down to the size of an apple, the crust we live upon would be thinner than the apple's peel. On average, the continental crust is about 30 to 50 kilometers thick, while the oceanic crust measures only 5 to 10 kilometers. Compared to Earth's total diameter of nearly 13,000 kilometers, this outer shell is remarkably delicate. Yet it is this thin layer that holds every mountain, every ocean, and every living thing. Beneath it lies a vast interior of hot, flowing rock and metal that we will never directly touch. It is humbling to realize that everything we know exists upon such a fragile skin, floating gently on the churning depths below. Earth's core is hotter than the surface of the sun. Deep at the center of our planet lies a core of iron and nickel, heated to temperatures exceeding 5,000 degrees Celsius. That is hotter than the surface of the sun, which burns at around 5,500 degrees. This immense heat is left over from the violent formation of Earth billions of years ago, combined with the ongoing decay of radioactive elements. The inner core remains solid despite this heat because of the crushing pressure at those depths, while the outer core flows as liquid metal. It is this swirling molten iron that generates Earth's magnetic field, shielding us from harmful cosmic radiation. All of this heat and motion happens silently beneath our feet, powering the restless geology of our world. There may be a whole ocean hidden deep inside the mantle. Scientists have discovered minerals deep within the Earth that contain vast amounts of water locked inside their crystal structures. One particular mineral called ringwoodite, found in the transition zone between the upper and lower mantle, can hold significant quantities of water within its atomic lattice. Some estimates suggest there may be more water trapped down there than in all the oceans on the surface combined. This hidden reservoir does not exist as liquid seas, but as water molecules bound within rock. If released, it would reshape our understanding of Earth's water cycle entirely. The idea of an ocean buried 700 kilometers beneath our feet is both strange and wonderful. A secret sea we may never see, but that quietly influences our planet's behavior. Rocks deep underground can flow like putty under pressure. We tend to think of rock as hard and unchanging, but deep within the Earth, intense heat and pressure transform solid stone into something almost fluid. In the mantle, rocks behave like extremely thick honey, flowing slowly over millions of years. This process is called plastic deformation, and it allows the mantle to convect, carrying heat from the core toward the surface. These slow currents are what drive the movement of tectonic plates above. A piece of mantle rock might take millions of years to complete a single cycle from deep to shallow and back again. It is geology on a timescale we can barely comprehend, where stone itself becomes patient and flowing. Earth's surface is constantly recycling through plate tectonics. The ground beneath us is not permanent. Through the process of plate tectonics, Earth's surface is continuously destroyed and renewed. At mid-ocean ridges, new crust forms as molten rock rises from below and solidifies. At subduction zones, old oceanic crust plunges back into the mantle, melting and eventually returning to the depths. This cycle takes roughly 200 million years for oceanic crust, meaning no part of the ocean floor is older than that. Continental crust lasts longer, but is still reshaped by collisions and rifting. The entire surface of our planet is slowly turning itself inside out, recycling rock like a vast, patient machine that has been running for billions of years. The continents we see today are pieces of ancient supercontinents. The familiar shapes of Africa, South America, and Australia are just the latest arrangement in a long history of continental wandering. Hundreds of millions of years ago, all the landmasses were joined together in supercontinents, with names like Pangaea, Rodinia, and even older ones we are still discovering. These giant landmasses formed, broke apart, and reformed multiple times throughout Earth's history. The evidence lies in matching coastlines, identical fossils found on opposite sides of oceans, and the patterns of ancient mountain ranges that once connected. The continents are still moving today, drifting centimeter by centimeter across the face of the planet. In another few 100 million years, they will come together once again, in a new configuration we cannot yet imagine. The rocks beneath your feet are the planet's memory written in stone. Every rock tells a story. Sedimentary rocks record ancient seas, river deltas, and desert dunes. Igneous rocks remember the moment they cooled from liquid fire. Metamorphic rocks bear witness to the intense pressures and temperatures they endured deep underground. Together, they form a record of Earth's history stretching back billions of years. Geologists read this record like a book, deciphering the tales of vanished oceans, extinct volcanoes, and long-gone mountain ranges. The ground beneath your feet is not just solid matter, but a chronicle of cosmic collisions, tectonic shifts, and the slow dance of continents. You are standing upon the planet's memory, written in layers of stone that have been accumulating since the world was young. Continents float like rafts on molten rock. supercontinents do not rest on solid ground. Instead, they float upon the asthenosphere, a layer of hot, partially molten rock that behaves almost like thick fluid over geological time. The lithosphere, which includes the crust and upper mantle, forms rigid plates that ride upon this flowing layer beneath. Just as a wooden raft floats on water, continents drift slowly across the planet's surface. The asthenosphere is not truly liquid, but under immense pressure and heat it can deform and flow, carrying the plates above it. This simple principle explains how land masses can travel thousands of kilometers over millions of years, rearranging the face of the Earth again and again. Continents drift as fast as fingernails grow. The pace of continental drift is extraordinarily slow by human standards, typically just a few centimeters per year. This happens to be roughly the same rate at which your fingernails grow. Over a single human lifetime, continents might move a meter or two, far too little to notice. But over millions of years, this gentle motion adds up to vast distances. Africa and South America, once joined, have separated by thousands of kilometers since the breakup of Pangaea. India traveled from the southern hemisphere all the way to collide with Asia. The slow, patient movement of continents is one of geology's most profound discoveries, revealing that nothing on Earth's surface is truly permanent. There have been at least 6 supercontinents before ours. Pangaea is the most famous supercontinent, but it was not the first. Geologists have identified evidence for at least 6 major supercontinents that formed and broke apart throughout Earth's history. Before Pangaea came Pannotia, and before that Rodinia, Columbia, Knorland, and perhaps others whose traces have been almost entirely erased by time. Each supercontinent assembled over hundreds of millions of years as plates collided, then eventually rifted apart and scattered across the globe. This cycle has repeated itself again and again, driven by the convection currents in the mantle below. The continents we see today are simply the latest pieces in an ancient puzzle that has been assembling and disassembling for billions of years. Pangaea was only the most recent supercontinent. Around 300 million years ago, all of Earth's major landmasses came together to form Pangaea, a supercontinent whose name means all lands. It stretched from pole to pole, surrounded by a single vast ocean called Panthalassa. Dinosaurs roamed freely across this connected world, and the climate was dramatically different from today. But Pangaea was not special in Earth's history. It was simply the most recent supercontinent, the one we have the best evidence for, because its breakup happened relatively recently in geological terms. Before it, others came and went, each shaping the course of evolution and climate in ways we are still working to understand. The next supercontinent may already be forming under the Pacific. The dance of the continents has not stopped. Right now, the Atlantic Ocean is widening, while the Pacific is slowly shrinking. Scientists predict that in roughly 200 to 300 million years, the continents will converge once again to form a new supercontinent. Some models suggest it will form as the Americas collide with Asia, closing the Pacific entirely. Others predict Africa and Europe will merge first. This future supercontinent has been given tentative names like Pangaea Ultima or Amasya. Though none of us will live to see it, the forces that will create it are at work beneath our feet at this very moment, patient and unstoppable. Australia is drifting north toward Asia every single year. Of all the continents, Australia is one of the fastest movers. It travels northward at roughly 7 centimeters per year, carried by the same tectonic forces that drive all continental motion. At this rate, Australia will eventually collide with Southeast Asia, perhaps merging with Indonesia or the Philippines in distant geological time. This collision will create new mountain ranges and reshape the geography of the region entirely. Already, the leading edge of the Australian plate is grinding against the islands to its north, generating earthquakes and volcanic activity. The journey north is slow, but it is relentless, and in 50 million years the map of that region will look entirely different. Africa may one day split into two separate continents. A massive rift is slowly tearing through East Africa, and it may eventually split the continent in two. The East African Rift System stretches thousands of kilometers from the Red Sea down through Ethiopia, Kenya, and Tanzania. In some places, the ground has already dropped by hundreds of meters, creating deep valleys and lakes. Volcanic activity along the rift hints at the molten rock rising from below. If this process continues, a new ocean basin will form, separating the Somali plate from the rest of Africa. The timescale is immense, perhaps 10 million years or more, but the process has already begun. Africa, the cradle of humanity, may one day become two separate landmasses drifting apart. Continents have collided and split apart many times in Earth's past. The history of Earth is a story of continental assembly and dispersal repeated countless times. Continents collide, building enormous mountain ranges where they meet. Then internal forces tear them apart, creating rift valleys and new ocean basins. The Appalachian Mountains in North America and the Scottish Highlands in Britain were once part of the same ancient range, formed when continents collided and later separated. The Himalayas are the result of India crashing into Asia. The Atlantic Ocean opened when the Americas pulled away from Europe and Africa. This cycle continues today and will continue for as long as Earth's interior remains hot enough to drive the motion of the plates. Some mountains are still rising faster than fingernails grow. Mountains may appear timeless and unchanging, but many are still actively growing. In the most tectonically active regions, uplift rates can exceed a centimeter per year, faster than the rate at which your fingernails grow. The Southern Alps of New Zealand, for example, rise at approximately 10 millimeters annually. This growth is the result of ongoing collisions between tectonic plates, pushing rock upward with immense force. Of course, erosion works against this rise, wearing the peaks down even as they climb. The battle between uplift and erosion determines the final height of any mountain range. It is a slow, silent struggle that has shaped Earth's landscapes for billions of years. The Himalayas are still growing every year. The collision between India and Asia that created the Himalayas has not stopped. Each year, the Indian subcontinent pushes northward at a rate of roughly 5 centimeters, driving the Himalayan peaks higher. Mount Everest, already the tallest point on Earth, grows by several millimeters annually. The forces involved are staggering, crumpling the crust and thickening it into towering ranges. This process has been underway for about 50 million years and shows no signs of slowing. Eventually, millions of years from now, erosion may win and the Himalayas will shrink. But for now, they continue their patient climb toward the sky, millimeter by millimeter. There are mountains higher than Everest hidden beneath the sea. When measured from base to summit, rather than from sea level, some underwater mountains dwarf Everest. Mauna Kea, in Hawaii, rises over 10,000 meters from the ocean floor, far exceeding Everest's height above sea level. The mid-ocean ridges, stretching for tens of thousands of kilometers across the seafloor, include peaks that rival any on land. These submarine mountains are formed by volcanic activity and the spreading of tectonic plates. We rarely think of them because they lie hidden beneath the waves, but they are among the most dramatic geological features on the planet. The ocean conceals an entire world of towering peaks and deep valleys, that few humans have ever seen. Earth's deepest point is nearly as far below sea level as planes fly above it. The Challenger Deep, located in the Mariana Trench, plunges nearly 11,000 meters below the ocean's surface. That is almost as deep as commercial aircraft fly high. If you placed Mount Everest at the bottom of the Challenger Deep, its peak would still be more than 2 kilometers underwater. The pressure at these depths is crushing, over 1,000 times the atmospheric pressure at the surface. Yet even here, life persists in the form of strange, resilient creatures adapted to the darkness and pressure. The Mariana Trench is a reminder that Earth's extremes extend both upward and downward, and that we live on only a thin slice of a vast vertical world. Entire mountain ranges have vanished without a trace. Mountains that once rivaled the Himalayas have been completely eroded away over geological time. The Appalachian Mountains in eastern North America were once as tall as the Alps, formed during ancient continental collisions hundreds of millions of years ago. Today, they are gently rolling hills, worn down by rain, wind, and ice. The same fate awaits all mountains eventually. Given enough time, even the mightiest peaks will crumble to sand and wash into the sea. The rocks that remain tell the story of these vanished giants, holding clues to their former glory in their mineral structure and the patterns of ancient sediments. Earthquakes can permanently change the length of a day. When massive earthquakes shift enormous amounts of rock, they can alter Earth's rotation. The magnitude 9 earthquake that struck Japan in 2011 redistributed enough mass to shorten the day by about 1.8 microseconds. Similarly, the 2004 Indian Ocean earthquake changed the length of the day by a few microseconds. These changes are far too small for us to notice, but they are measurable with precise instruments. It is a striking reminder that the energy released by major earthquakes is not just destructive, but can affect the fundamental properties of our planet. The Earth's rotation, which seems so constant, is subtly shaped by the geological forces churning below. Every volcano connects to a hidden magma chamber below. Beneath every volcano lies a reservoir of molten rock called a magma chamber. These chambers form when rock melts deep in the earth and rises toward the surface, pooling in pockets within the crust. The magma can sit there for thousands or even millions of years, slowly cooling or gradually accumulating more molten material. When pressure builds beyond what the overlying rock can contain, an eruption occurs. The size and shape of these chambers vary enormously, from small pools feeding minor vents to vast reservoirs capable of producing supervolcanic eruptions. Understanding these hidden chambers is crucial to predicting volcanic activity, yet they remain largely invisible, detectable only through the subtle signals they send to the surface. Some volcanic eruptions can last for hundreds of thousands of years. Not all volcanic eruptions are brief, explosive events. Some have continued for staggeringly long periods of time. The Deccan Traps in India represent a volcanic province created by eruptions that lasted for hundreds of thousands of years, around 66 million years ago. During this time, vast floods of lava poured across the landscape, layer upon layer, eventually covering an area larger than modern France. Similar flood basalt events have occurred throughout Earth's history, often coinciding with major extinctions. These prolonged eruptions release enormous amounts of gases into the atmosphere, altering climate and reshaping ecosystems on a global scale. They are volcanoes on a timescale we can barely comprehend. Yellowstone hides one of the largest volcanic systems on Earth. Beneath the famous geysers and hot springs of Yellowstone National Park lies one of the largest active volcanic systems on the planet. The Yellowstone hotspot has produced 3 major caldera-forming eruptions in the past 2 million years, each far more powerful than any eruption in recorded human history. The most recent, about 640,000 years ago, ejected roughly 1,000 cubic kilometers of material. The magma chamber beneath Yellowstone still feeds the geothermal features that draw millions of visitors each year. While another massive eruption is not expected anytime soon, the system remains active, a reminder of the immense power sleeping beneath some of Earth's most beautiful landscapes. Supervolcanoes can alter the planet's climate for centuries. When supervolcanoes erupt, they release enough ash and gas to affect the entire planet. The eruption of Mount Tambora in 1815 caused the year without a summer, bringing crop failures and famine to distant continents. Even larger eruptions in the geological past have had far more dramatic effects. The Toba eruption about 74,000 years ago may have caused a volcanic winter lasting years, potentially reducing the human population to dangerously low levels. Supervolcanic events inject massive amounts of sulfur dioxide into the stratosphere, where it forms aerosols that reflect sunlight and cool the planet. The resulting climate disruption can last for decades or even centuries, reshaping ecosystems and altering the course of evolution. The largest known volcanic eruption happened in Indonesia. The eruption of Tambora in 1815 remains the largest volcanic event in recorded human history. Located on the island of Sumbawa in Indonesia, Tambora exploded with a force that killed tens of thousands of people directly and caused global climate disruption. But even Tambora was modest compared to some prehistoric events. The eruption of Toba, also in Indonesia, about 74,000 years ago, was far larger, possibly one of the most powerful eruptions in the past 2 million years. Indonesia sits on the Pacific Ring of Fire, where tectonic activity makes it one of the most volcanically active regions on Earth. Its history is written in layers of ash and the memories of catastrophic explosions. Lava lakes can remain molten for decades without cooling. In a few places on Earth, volcanoes maintain persistent lakes of molten lava that churn and glow year after year. The lava lake at Kilauea in Hawaii existed for decades before draining in 2018, and similar features exist at Erta Ale in Ethiopia and Mount Nyiragongo in the Democratic Republic of Congo. These lakes form when a continuous supply of magma from below keeps the surface molten despite heat loss to the air. The sight of glowing orange lava bubbling and flowing is mesmerizing, a window into the molten interior of the planet. These lakes are rare and precious, offering scientists a unique opportunity to study volcanic processes in real time. Lightning can strike inside volcanic ash clouds. During powerful eruptions, volcanic lightning illuminates the ash plumes in spectacular displays. This phenomenon occurs when ash particles collide within the eruption column, generating static electricity much like ice particles do in thunderclouds. The result is bolts of lightning crackling through the dense, roiling ash, sometimes accompanied by the glow of molten rock below. Volcanic lightning was famously observed during the eruptions of Eyjafjallajökull in Iceland and Sakurajima in Japan. It is a reminder that volcanoes are not just geological events but atmospheric ones as well, capable of creating their own weather and electrical storms as they reshape the land. When volcanoes meet ice, they create explosive steam eruptions. When hot magma encounters ice or water, the result can be extraordinarily violent. The rapid conversion of water to steam generates immense pressure, causing explosive eruptions far more powerful than the magma alone would produce. These phreatomagmatic eruptions can blast rock and ash high into the atmosphere. In Iceland, where volcanoes often lie beneath glaciers, such events can trigger devastating floods called Jökulhlaups as meltwater pours out from under the ice. The combination of fire and ice creates some of the most dramatic volcanic phenomena on Earth, a reminder that the interaction of different geological systems can produce effects far greater than either alone. Entire new islands have risen from volcanic eruptions within living memory. Volcanic islands can emerge from the sea with startling speed. Surtsey, off the coast of Iceland, rose from the ocean between 1963 and 1967, created entirely by volcanic eruptions during that brief period. It became a natural laboratory for scientists studying how life colonizes new land. More recently, submarine eruptions near Tonga have created temporary islands that emerged, eroded, and sometimes vanished again within years. These events remind us that the map of the world is not fixed. New land can appear at any moment, wherever the restless forces beneath the ocean decide to build. Some eruptions have left ash that still circles the globe today. Major volcanic eruptions inject fine ash and aerosols into the upper atmosphere, where they can remain suspended for years. The eruption of Mount Pinatubo in 1991 released enough material to lower global temperatures by about 0.5 degrees Celsius for over a year. Traces of ash from ancient eruptions have been found in ice cores from Greenland and Antarctica, preserved in layers that correspond to known events millions of years ago. These tiny particles circle the Earth on high-altitude winds, slowly settling out over time. Long after the eruption itself is over, its signature remains in the atmosphere and in the geological record, a ghostly reminder of its power. Granite once flowed like molten rivers beneath the surface. The granite that forms the cores of mountain ranges and the foundations of continents was once liquid. Deep beneath the surface, temperatures and pressures caused rock to melt, forming magma that rose slowly through the crust. When this magma cooled underground without ever reaching the surface, it crystallized into granite, a coarse-grained rock, speckled with minerals like quartz, feldspar, and mica. The slow cooling allowed large crystals to form, giving granite its characteristic texture. Today, when we see granite exposed at the surface, we are looking at rock that formed kilometers underground, now revealed only because the rock above it has eroded away over millions of years. Basalt covers most of the ocean floor in dark, dense layers. While granite dominates the continents, basalt is the rock of the ocean floor. This dark, dense volcanic rock forms when lava erupts at mid-ocean ridges and cools rapidly upon contact with seawater. The entire floor of the Atlantic, Pacific, and Indian Oceans is paved with layer upon layer of basalt, constantly renewed as new rock rises at the ridges and old rock is subducted back into the mantle. Basalt is rich in iron and magnesium, giving it its characteristic dark color. It is one of the most common rocks on Earth, yet because most of it lies hidden beneath the waves, we rarely encounter it compared to the continental rocks we walk upon daily. Pillow lava freezes in shapes that look like underwater balloons. When lava erupts on the ocean floor, the outer surface cools almost instantly upon contact with cold seawater, forming a glassy skin. But the interior remains molten, and as more lava pushes through, it inflates the cooling shell like a balloon. The result is rounded, pillow-shaped formations that pile up on top of one another. These pillow lavas are found wherever volcanic activity has occurred underwater, from mid-ocean ridges to the flanks of volcanic islands. Ancient pillow lavas exposed on land tell geologists that the rock once formed beneath the sea, providing valuable clues about the geological history of a region. Obsidian is volcanic glass cooled in an instant. When lava cools so rapidly that crystals have no time to form, The result is obsidian, a natural volcanic glass. This typically happens when lava flows into water or erupts in thin sheets that lose heat quickly to the air. Obsidian is smooth, dark, and often has a conchoidal fracture pattern that produces sharp edges. Ancient humans prized it for making tools and weapons because of those razor-sharp edges. Chemically, obsidian is similar to granite, but its glassy texture makes it entirely different in appearance. It is a reminder that the same molten rock can produce vastly different results depending on how quickly it cools. Some rocks preserve bubbles of Earth's ancient atmosphere. Certain volcanic rocks contain tiny gas bubbles that were trapped as the lava cooled. These vesicles, as geologists call them, can preserve samples of the gases present when the rock formed. In some ancient rocks billions of years old, scientists have analyzed these bubbles to understand what Earth's early atmosphere was like. The results show a world very different from today, with little oxygen and abundant carbon dioxide and other gases. These frozen bubbles are time capsules, preserving the breath of a young planet long before the first forests or animals existed. Flood basalt eruptions have caused mass extinctions in the past. Throughout Earth's history, massive volcanic events have poured unimaginable quantities of lava across entire continents. These flood basalt eruptions lasted for hundreds of thousands of years, releasing toxic gases and reshaping the climate. The Siberian traps, formed around 250 million years ago, coincided with the largest mass extinction in Earth's history, when over 90% of marine species vanished. The Deccan traps in India erupted around the same time as the dinosaurs disappeared, and some scientists believe they contributed to that extinction as well. These events show that volcanism can be both a creator and destroyer of life on a planetary scale. Ash from ancient eruptions still lies buried in modern soils. Long after a volcanic eruption has ended, its legacy remains in the ground. Layers of ash from prehistoric eruptions are preserved in sediments around the world, sometimes forming distinct bands that geologists can identify and date. In some cases, ancient ash layers provide crucial time markers, allowing scientists to correlate rock formations across vast distances. The ash itself weathers over time, releasing nutrients into the soil and contributing to the fertility of volcanic regions. Even today, farmers in places like the slopes of Mount Vesuvius benefit from soils enriched by eruptions thousands of years ago. Earthquakes can make entire rivers run backward. During the New Madrid earthquakes of 1811 and 1812, the Mississippi River briefly flowed backward as the land itself shifted and tilted. Witnesses reported waterfalls appearing where none had existed, and boats were thrown violently as the river churned. These earthquakes, among the most powerful in North American history, temporarily changed the landscape so dramatically that the river's normal flow was reversed. Similar effects have been observed in other major earthquakes, where ground deformation alters drainage patterns. It is a reminder that even something as seemingly permanent as the course of a river can be changed in moments by the forces deep within the earth. Some faults creep silently, without any shaking at all. Not all fault movement produces earthquakes. In some places, tectonic plates slide past each other in a slow, continuous motion called fault creep. The Hayward Fault in California, for example, creeps at a rate of several millimeters per year, gradually offsetting roads, fences, and building foundations without generating significant seismic events. This creep releases tectonic stress slowly rather than suddenly, potentially reducing the likelihood of major earthquakes. However, creeping faults can still produce damaging quakes if sections become locked and stress accumulates. Geologists monitor these subtle movements carefully, using precise instruments to track the slow, silent slippage of the Earth's crust. The ground beneath us is constantly shifting in small ways. Even when we feel nothing, the ground is in motion. Micro-earthquakes, too small to perceive without instruments, occur continuously around the world. Tectonic stresses build and release in countless tiny adjustments, each one recorded by sensitive seismometers. Temperature changes cause rock to expand and contract. Water seeping through underground layers shifts sediments and dissolves minerals. The tides pull at the land, causing it to rise and fall by centimeters twice a day. The solid Earth we take for granted is in fact a dynamic system, constantly responding to forces both internal and external, always moving even when we cannot feel it. Major earthquakes can shift the sea floor by several meters. When large earthquakes occur beneath the ocean, the sudden displacement of the seafloor can raise or lower entire sections by several meters. The 2011 Tohoku earthquake off Japan moved portions of the seafloor horizontally by up to 50 meters and vertically by several meters. This massive displacement is what generates tsunamis, as the water above the shifted seafloor is suddenly pushed upward and outward. The energy released travels across entire ocean basins, reaching distant shores hours after the quake. These undersea shifts are among the most powerful geological events on Earth, capable of reshaping coastlines and devastating communities thousands of kilometers away. Tectonic plates slip beneath each other at subduction zones. At subduction zones, one tectonic plate dives beneath another and descends into the mantle. This process drives some of the most powerful earthquakes and volcanic activity on Earth. The subducting plate carries water and sediments down with it, eventually releasing them as the rock heats up. This water lowers the melting point of the overlying mantle, triggering the formation of magma and feeding volcanic arcs, like those around the Pacific Ring of Fire. The friction between the plates as one slides beneath the other can lock, building up stress until it releases in devastating megathrust earthquakes. Subduction zones are among the most geologically active places on the planet. The planet hums with micro-earthquakes you never feel. At any given moment, dozens of small earthquakes are occurring around the world. Most are too weak to be felt, registering only on sensitive seismometers operated by geological surveys. These micro-earthquakes are constantly adjusting stresses in the crust, releasing tiny amounts of energy that would otherwise accumulate. They occur along fault lines, near volcanoes, and even in areas far from tectonic boundaries. Some are triggered by human activities, like mining or reservoir filling. Together, they form a constant background hum of seismic activity, a reminder that the Earth is never truly still, but always shifting and adjusting in ways we cannot perceive. Shockwaves from massive quakes travel all the way around the globe. When a major earthquake strikes, the energy radiates outward in all directions as seismic waves. These waves travel through the Earth's interior, reflecting and refracting as they pass through different layers of rock and metal. Sensitive seismometers on the opposite side of the planet can detect arrivals from distant earthquakes, recording the patterns of waves that have traveled thousands of kilometers through the deep Earth. Scientists use these recordings to study the internal structure of the planet, mapping the boundaries between crust, mantle, and core. Every major earthquake becomes a natural experiment, sending signals through the Earth that reveal secrets we could not otherwise discover. Some earthquakes release energy equivalent to millions of tons of TNT. The energy released by major earthquakes is almost incomprehensible. The magnitude 9 earthquake that struck Chile in 1960, the most powerful ever recorded, released energy equivalent to roughly 25 billion tons of TNT. Even smaller quakes, in the magnitude 7 range, release energy comparable to nuclear explosions. This energy has been accumulating for centuries as tectonic plates strain against each other, stored in the elastic deformation of rock. When the stress finally exceeds the strength of the rock, it releases all at once, sending devastating waves through the ground. It is the sudden release of millions of years of geological patience compressed into a few terrifying seconds. The ocean floor is younger than the continents. While continents preserve rocks that are billions of years old, the ocean floor is surprisingly young in geological terms. The oldest oceanic crust is only about 200 million years old, compared to continental rocks that date back nearly 4 billion years. This dramatic age difference exists because the ocean floor is constantly being recycled. New crust forms at mid-ocean ridges, where magma rises from the mantle and solidifies. That same crust eventually slides beneath continents at subduction zones, returning to the mantle to be melted and reformed. The ocean floor is like a giant conveyor belt, perpetually renewing itself while the continents remain as ancient, floating passengers on the surface of our dynamic planet. Magnetic stripes on the seafloor record Earth's magnetic flips. When scientists first mapped the magnetism of the ocean floor, they discovered a remarkable pattern. Symmetrical stripes of alternating magnetic polarity extend outward from mid-ocean ridges like zebra stripes. These stripes form because molten rock rising at ridges records the magnetic field direction as it cools and solidifies. When the field reverses, new rock records the opposite polarity. Over millions of years, this creates a barcode-like pattern frozen into the seafloor. These magnetic stripes provided crucial evidence for plate tectonics and seafloor spreading. They also serve as a timeline, allowing scientists to determine the age of oceanic crust and calculate how fast the plates are moving, typically a few centimeters per year. The sea spreads outward from the mid-Atlantic ridge like a conveyor belt. The Atlantic Ocean grows wider by about 2.5 centimeters each year as new crust forms at the mid-Atlantic ridge. This underwater mountain range runs north to south through the center of the Atlantic, marking where the American plates are pulling away from the European and African plates. Magma rises from the mantle to fill the gap, cooling and hardening into fresh oceanic crust. As new rock forms at the ridge, older rock is pushed outward on both sides. This process, called seafloor spreading, has been widening the Atlantic for about 180 million years. Europe and North America, once neighbors, now sit thousands of kilometers apart across an ever-expanding ocean. The Atlantic Ocean was once just a long rift valley. Before the Atlantic existed, the supercontinent Pangaea stretched across the globe. About 200 million years ago, this landmass began to tear apart. The initial break was a rift valley, similar to the East African rift we see forming today. Magma rose through cracks in the stretching crust, volcanic activity intensified, and the land slowly pulled apart. Eventually, the rift opened wide enough for seawater to flood in, creating a narrow seaway. Over millions of years, continued spreading widened this seaway into the Atlantic Ocean. Evidence of this ancient rifting can still be found in the matching geological formations on opposite sides of the Atlantic, from the mountains of Scotland to those of Appalachia. Iceland sits directly above a tear in Earth's crust. Iceland is one of the few places on Earth where a mid-ocean ridge rises above sea level. The island straddles the boundary between the North American and Eurasian plates, which are pulling apart at a rate of about 2 centimeters per year. This rifting creates a landscape of dramatic fissures, hot springs, and volcanic activity. The island is literally being torn in two, with the western part moving toward North America and the eastern part toward Europe. Thingvellir, a rift valley in Iceland, is a visible expression of this separation, where visitors can walk between cliffs that are slowly pulling apart. Iceland is geology in action, a window into the forces that shape our planet's surface. The Hawaiian Islands are a moving chain built by a stationary hotspot. The Hawaiian Islands stretch across the Pacific in a long line, each island older than the one to its southeast. This pattern exists because the Pacific Plate is moving over a stationary hotspot, a plume of exceptionally hot rock rising from deep in the mantle. As the plate drifts northwest at about 7 centimeters per year, the hotspot punches through and builds new volcanoes. The Big Island of Hawaii, the youngest and most volcanically active, sits directly over the hotspot today. Islands further northwest, like Kauai and beyond, have moved off the hotspot and become dormant. The chain extends underwater as seamounts, forming a trail of volcanic evidence stretching back millions of years. Mid-ocean ridges stretch for tens of thousands of miles. The global mid-ocean ridge system is the longest mountain range on Earth, extending over 65,000 kilometers across the ocean floors. It winds through every major ocean, from the Atlantic to the Indian to the Pacific, forming a continuous chain of underwater mountains. At these ridges, tectonic plates pull apart, and new oceanic crust is born. The ridge itself rises several kilometers above the surrounding seafloor, with a central rift valley where volcanic activity is concentrated. Hydrothermal vents along these ridges support unique ecosystems in total darkness. This vast mountain range, largely hidden from view beneath the waves, represents the most active geological feature on our planet, constantly reshaping the ocean floor. Crystals can grow larger than a person inside underground caves. Deep beneath the Chihuahuan Desert in Mexico lies a chamber filled with crystals of staggering size. Some of these selenite crystals reach lengths of over 11 meters and weigh more than 50 tons. They grew so large because of the exceptional conditions in the cave, which remained filled with mineral-rich water at a constant temperature for hundreds of thousands of years. The cave was so hot, around 50 degrees Celsius, that entering without protective cooling suits would be fatal within minutes. These giant crystals are among the most remarkable geological formations ever discovered, proving that under the right conditions, and given enough time, nature can create structures that defy imagination. Giant gypsum crystals shimmer in Mexico's Cave of the Crystals. The Cave of the Crystals, or Cueva de los Cristales, was discovered accidentally in 2000 by miners drilling in the Nika mine. What they found was a geological wonder, a chamber adorned with massive gypsum crystals that refracted light into shimmering rainbows. The crystals are made of selenite, a transparent variety of gypsum, and they formed over approximately 500,000 years as hot mineral-saturated water slowly deposited layer upon layer of crystal. The discovery opened a window into the slow, patient processes that shape the underground world. Today, the cave remains largely inaccessible, flooded once more to protect these extraordinary formations for future generations. Stalactites grow from the ceiling, stalagmites from the floor. In caves around the world, water seeping through limestone creates delicate stone formations over thousands of years. Stalactites hang from ceilings like icicles, formed as mineral-laden water drips down and leaves behind traces of calcium carbonate. Each drop deposits a tiny ring of mineral, gradually building a hollow tube that thickens into a cone. Below, where those drops fall and splash, stalagmites rise from the floor, building upward layer by layer. Sometimes stalactites and stalagmites meet in the middle, forming columns that span from floor to ceiling. These formations are the product of immense patience, each centimeter representing centuries of slow, steady growth in the darkness underground. Cave formations grow slower than fingernails. The growth rate of stalactites and stalagmites is extraordinarily slow, typically less than a millimeter per year under ideal conditions. Some formations may only grow a fraction of a millimeter over a century, meaning that a stalactite the length of your arm could represent tens of thousands of years of continuous formation. This slow pace depends on factors like water flow, mineral concentration, and temperature. Human activities such as touching formations can halt growth entirely, as oils from skin seal the porous surface. The immense age of cave formations makes them invaluable records of past climate conditions, with their chemical composition preserving information about rainfall and temperature stretching back millennia. Some caves have their own weather systems. Large cave systems can develop distinct internal climates that differ dramatically from conditions on the surface. Temperature differences between cave openings create air currents that flow through passages like wind. Humidity levels can reach nearly 100%, creating mist and fog in certain chambers. Some caves experience barometric breathing, where changes in external air pressure cause air to flow in or out of entrances. In the largest systems, temperature inversions can trap cold air in lower passages, while warmer air rises to upper levels. These underground weather patterns affect everything from crystal formation to the survival of cave-adapted species that depend on stable conditions. Earth's longest cave stretches for hundreds of miles underground. Mammoth Cave in Kentucky holds the record as the longest known cave system on Earth, with over 670 kilometers of surveyed passages. Explorers continue to discover new sections, and the total length grows year after year. The cave formed over millions of years, as mildly acidic groundwater dissolved the limestone bedrock, carving out an intricate network of tunnels, chambers, and underground rivers. Some passages are vast enough to accommodate buildings, while others are tight squeezes that only the most dedicated cavers can navigate. Mammoth Cave is a labyrinth beneath the surface, a hidden world of darkness and silence that rivals any surface landscape in complexity and scale. Karst landscapes hide secret rivers flowing through stone. Karst topography forms when soluble bedrock like limestone dissolves over time, creating landscapes riddled with sinkholes, caves, and underground drainage systems. Rivers that flow on the surface may suddenly disappear into swallow holes, continuing their journey through hidden passages beneath the earth. These underground rivers can travel for kilometers before emerging at springs miles away. The water carves out caverns and tunnels as it flows, constantly reshaping the subterranean landscape. Karst regions cover about 15% of Earth's land surface and are home to some of the most spectacular cave systems in the world, from the cenotes of Mexico to the underground rivers of Slovenia. Sinkholes can swallow buildings in seconds. When underground cavities in limestone or other soluble rock grow too large, the surface above can collapse suddenly and catastrophically. These sinkholes can appear without warning, swallowing cars, roads, and even entire buildings in moments. The collapse happens when the thin roof of rock or soil over an underground void can no longer support its own weight. Sinkholes are common in karst regions and can be triggered by heavy rainfall, drought, or human activities, like pumping groundwater. The Qattara Depression in Egypt and the Great Blue Hole in Belize are both giant sinkholes formed over geological time, reminders of the hidden voids that exist beneath our feet. Hydrothermal vents create black smokers on the ocean floor. Deep beneath the waves, where tectonic plates pull apart, superheated water erupts from the seafloor in dramatic plumes. These black smokers get their name from the dark, mineral-rich fluid that billows out like underwater smoke. The water, heated to temperatures over 400 degrees Celsius, carries dissolved metals and minerals from deep within the Earth's crust. When this superheated fluid meets the near-freezing ocean water, the minerals precipitate instantly, creating towering chimney structures. These black smokers can grow several meters tall in just a few years, forming jagged spires of metal sulfides in the eternal darkness of the deep. They are windows into the chemical processes occurring beneath the seafloor. Those vents support entire ecosystems without sunlight. In the perpetual darkness of the deep ocean, hydrothermal vents host thriving communities of life that exist without any input from the sun. Instead of photosynthesis, these ecosystems are powered by chemosynthesis, where bacteria convert chemicals from the vent fluid into energy. Giant tube worms, some over 2 meters long, cluster around the vents, housing symbiotic bacteria in their bodies. Blind shrimp, ghostly crabs, and strange fish crowd the mineral-rich waters. These ecosystems challenged our understanding of where life can exist, demonstrating that sunlight is not a universal requirement. Some scientists believe similar vents could support life on ocean moons like Europa and Enceladus. Minerals there build chimneys taller than houses. The chimneys that form at hydrothermal vents can reach remarkable sizes, sometimes growing to heights of over 20 meters. They form as dissolved minerals in the superheated vent fluid precipitate upon contact with cold seawater. Layers of copper, zinc, iron, and sulfide compounds accumulate rapidly, building intricate structures in the darkness. Some chimneys grow several centimeters per day, among the fastest mineral formation rates on Earth. These structures are incredibly fragile despite their size, collapsing and rebuilding constantly as conditions change. The mineral deposits around hydrothermal vents are so rich that they have attracted interest from deep-sea mining companies, raising questions about the environmental costs of extracting these resources. Some lakes contain dissolved carbon dioxide that can erupt like soda. In certain volcanic regions, lakes can accumulate vast quantities of dissolved carbon dioxide in their deep waters. These lakes become like giant bottles of soda, with enormous amounts of gas held in solution by the pressure of the water above. If the stratification of the lake is disturbed by an earthquake, landslide, or other event, the gas can suddenly come out of solution and erupt explosively. In 1986, Lake Nyos in Cameroon released a massive cloud of carbon dioxide that rolled down surrounding valleys, suffocating over 1,700 people and thousands of animals. This phenomenon, called limnic eruption, is one of the most unusual and deadly geological hazards on Earth. Life thrives at temperatures above 120 degrees Celsius near vents. The extreme environments around hydrothermal vents push the limits of what we thought possible for life. Certain microorganisms called hyperthermophiles not only survive, but actively grow at temperatures exceeding 120 degrees Celsius. Some species have been found living at 121 degrees, and there may be life at even higher temperatures we have yet to discover. These organisms possess special proteins and cell membranes adapted to withstand extreme heat. Their existence has expanded our understanding of the conditions under which life can exist, and has implications for the search for life on other worlds, where extreme temperatures are common. Natural diamonds take billions of years to form deep within the Earth. Diamonds form under extraordinary conditions, roughly 150 kilometers beneath the Earth's surface in the upper mantle. There, temperatures exceed 1,000 degrees Celsius, and pressures reach about 50,000 times atmospheric pressure at sea level. Under these extreme conditions, carbon atoms arrange themselves into the rigid crystal structure that makes diamonds the hardest natural material on Earth. Most natural diamonds are between 1 and 3 billion years old, having formed in ancient times when conditions were even more extreme. They reach the surface through violent volcanic eruptions that create kimberlite pipes, racing upwards so quickly that the diamonds have no time to convert back into graphite. Every gemstone tells the story of its geological birth. Each type of gemstone forms under specific conditions of pressure, temperature, and chemistry, making every gem a geological autobiography. The color, clarity, and crystal structure of a stone reveal the environment where it was created. Sapphires from Sri Lanka differ subtly from those of Madagascar because each formed under unique conditions. Inclusions within gems can contain traces of the fluids and minerals present during formation, sometimes including materials not found anywhere else on Earth. Gemologists can often determine where a stone originated based on these characteristics alone. When you hold a gemstone, you hold a piece of deep Earth history, a record of conditions that existed millions or billions of years ago. Rubies and sapphires are the same mineral colored by different elements. Rubies and sapphires are both varieties of the mineral corundum, which is aluminum oxide. In its purest form, corundum is colorless, but trace amounts of other elements create the stunning colors we associate with these precious stones. Chromium gives rubies their deep red color, while iron and titanium create the blue of sapphires. Other trace elements produce sapphires in colors ranging from pink to yellow to green. The crystal structure is identical in all cases, differing only in these tiny impurities. This geological coincidence means that a ruby and a blue sapphire, though they appear completely different, are essentially the same mineral with different atomic guests responsible for their distinct personalities. Emeralds form only under the rarest conditions of pressure and chemistry. Emeralds are among the rarest of all gemstones because they require an unusual combination of elements to form. They need beryllium, chromium, and vanadium, elements that rarely occur together in nature. Beryllium is typically found in continental crust, while chromium and vanadium are more common in oceanic crust. Only where these different rock types interact, often through tectonic collision or hydrothermal activity, can emeralds form. Most emeralds contain inclusions and fractures because of the turbulent conditions of their formation. A flawless emerald is rarer than a flawless diamond. This geological rarity, combined with their striking green color, has made emeralds prized throughout human history. Opal forms from ancient groundwater, seeping through silica rock. Opal is not a crystal but a solidified gel of silica and water. It forms when silica-rich groundwater seeps through sedimentary rock, depositing microscopic spheres of silica in cavities and cracks. Over millions of years, these spheres settle and compact, creating the solid opal we find today. The famous play of colors in precious opal comes from light diffracting through these regularly arranged spheres, like light through a prism. Australian opals formed in ancient inland seas that dried up about 100 million years ago. The process is so slow that it takes roughly 5 million years to form 1 centimeter of opal under natural conditions. Salt domes can pierce through rock like slow-motion explosions. Salt deposits buried deep underground behave strangely over geological time. Salt is less dense than the overlying rock, and under pressure it becomes plastic and begins to flow upward. Over millions of years, this buoyant salt can push through kilometers of overlying sediment, rising like a slow-motion balloon through denser material. The resulting salt domes can be several kilometers across and extend deep into the crust. They are important geological features, often trapping oil and gas in the deformed rock around them. The Gulf Coast of the United States is underlain by numerous salt domes that have been rising since the Jurassic period, creating both valuable resources and geological hazards. Petrified wood is actually quartz replacing wood atom by atom. When a tree is buried rapidly in volcanic ash or sediment, groundwater rich in dissolved silica can begin a remarkable transformation. The silica slowly infiltrates the wood's cellular structure, precipitating as quartz in spaces where organic material decays. Over millions of years, this process replaces the original wood with stone while preserving incredible detail. Growth rings, bark texture, and even individual cells can be seen in petrified wood, frozen in quartz. The colors come from trace minerals present during fossilization, with iron creating reds and yellows, manganese producing pink and orange. Arizona's petrified forest contains logs over 200 million years old, turned to rainbow-colored stone. Gold and platinum came from ancient meteor impacts. The gold and platinum that we mine today likely arrived on Earth through ancient cosmic bombardment. In the early solar system, dense metals like gold and platinum sank toward Earth's core along with iron, making them scarce in the crust. However, about 4 billion years ago, a period of intense asteroid impacts known as the Late Heavy Bombardment delivered fresh supplies of these precious metals to the surface. These cosmic gifts remained in the crust where we can now extract them. Without this ancient rain of meteorites, the gold in wedding rings, the platinum in catalytic converters, and other precious metals we value would be locked forever in Earth's unreachable core. Metamorphic rocks record the history of pressure and heat inside the planet. When existing rocks are subjected to intense pressure, extreme heat, or both, they transform into metamorphic rocks without melting. This process rearranges minerals, changes textures, and creates entirely new rock types. The conditions required for metamorphism typically occur deep within the Earth, in subduction zones, or near magma chambers. By studying metamorphic rocks at the surface, geologists can reconstruct the temperatures and pressures they experienced millions of years ago. Different minerals form at different conditions, acting like geological thermometers and pressure gauges. The metamorphic rock you pick up may have been buried 30 kilometers deep and heated to 700 degrees before tectonic forces brought it back to the surface. Slate was once mud pressed by time into stone. Slate begins its existence as fine-grained mud, settling layer upon layer at the bottom of ancient seas or lakes. Over millions of years, the weight of accumulating sediment compresses this mud into shale, a soft sedimentary rock. When tectonic forces bury shale deeper and subject it to increased pressure and mild heat, the clay minerals within begin to realign, forming the flat, parallel sheets characteristic of slate. This layered structure allows slate to be split into thin, flat pieces, making it ideal for roofing tiles and chalkboards. Every piece of slate you see was once soft mud at the bottom of a water body, transformed by the patient application of geological force over immense spans of time. Marble began its life as limestone filled with sea fossils. The gleaming marble used in sculptures and buildings started as ordinary limestone on ancient seafloors. Limestone forms from the accumulated shells and skeletons of marine organisms, layer upon layer of calcium carbonate settling over millions of years. When tectonic forces push this limestone deep into the earth, heat and pressure transform it into marble. The calcite crystals grow larger and interlock, erasing most traces of the original fossils while creating the smooth, crystalline texture that sculptors prize. The pure white marble of Carrara, used by Michelangelo for his greatest works, was once a reef teeming with life in a prehistoric sea. Every statue carries the echo of ancient marine creatures. Coal began as ancient forests, trapped in swampy worlds. 300 million years ago, during the Carboniferous period, vast swamp forests covered much of the land. When trees and plants died, they fell into oxygen-poor swamp water, where decomposition was incomplete. Layer upon layer of dead vegetation accumulated, forming thick deposits of peat. As sediments buried these peat layers, pressure and heat slowly transformed them into lignite, then bituminous coal, and eventually anthracite. The coal we burn today stores sunlight captured by trees hundreds of millions of years ago. Each ton of coal represents roughly 10 tons of ancient plant material, compressed and transformed by time into concentrated carbon. The forests of the Carboniferous live on as fuel. Oil comes from the buried remains of ancient plankton. The petroleum that powers modern civilization originated as microscopic marine organisms that lived hundreds of millions of years ago. When these plankton and algae died, their bodies sank to the seafloor and were buried by sediments. Over millions of years, heat and pressure transformed this organic material into kerogen, and eventually into liquid oil and natural gas. The oil then migrated through porous rock until it became trapped beneath impermeable layers, forming reservoirs. Each barrel of oil represents the concentrated remains of an unimaginable number of ancient microorganisms, their solar energy stored for eons. We are burning the compressed remnants of ancient sunlit seas. Every grain of sand tells the story of a vanished mountain. A single grain of sand is the survivor of an epic journey spanning millions of years. It began as part of a massive mountain, broken free by frost, wind, or rain. Tumbling down slopes and carried by rivers, the grain was rounded and reduced, weathered and worn. It may have been deposited in a beach or desert, only to be picked up again and carried further. The composition of sand reveals its origin: quartz from granite mountains, shell fragments from tropical reefs, volcanic glass from oceanic islands. By reading the mineralogy of sand, geologists can trace its path across continents and through geological epochs, each grain a tiny witness to the erosion of worlds. Fossils can capture raindrops that fell hundreds of millions of years ago. In some ancient rock formations, paleontologists have discovered something extraordinary: the imprints of individual raindrops preserved for hundreds of millions of years. These fossils formed when rain fell on soft mud or volcanic ash that then dried and hardened before being buried. The size and distribution of these ancient raindrop impressions can tell us about atmospheric conditions in deep time, including air density and the intensity of ancient storms. Such fossils are rare and delicate, preserved only when conditions were exactly right. They are among the most evocative traces of the past, connecting us directly to a moment when rain fell on an alien Earth, leaving marks that would outlast the mountains. Some fossils preserve soft tissues, even colors and feathers. While most fossils preserve only hard parts like bones and shells, extraordinary preservation sometimes captures soft tissues that normally decay. Feathered dinosaurs from China retain not just feather impressions but melanosomes, the pigment structures that reveal original colors. Some fossils contain traces of skin, internal organs, and even stomach contents. These exceptional specimens form under specific conditions, often rapid burial in fine-grained sediment with low oxygen. Such fossils revolutionize our understanding of ancient life, showing that dinosaurs came in patterns and colors, that ancient squid had ink sacs, and that soft-bodied creatures left traces we never expected to find. They open windows to lost worlds. Stromatolites record the oldest known life on Earth. Stromatolites are layered rock structures built by ancient colonies of cyanobacteria, among the earliest life forms on Earth. The oldest known stromatolites date back nearly 3.5 billion years, preserving evidence of life when the planet was young. These microbial communities grew in shallow waters, trapping sediment and building up layer after layer over time. Modern stromatolites still grow in a few places, like Shark Bay in Australia, offering a living glimpse of our planet's biological past. These humble mounds of rock represent one of the longest biological lineages on Earth, connecting us to the dawn of life when microbes first began to shape the planet. Banded iron formations mark the moment the planet began to breathe. Some of the most distinctive rocks on Earth are banded iron formations, striped layers of iron oxide alternating with silica. These rocks, mostly between 2 and 3 billion years old, record a pivotal moment in Earth history. Early photosynthetic organisms began releasing oxygen as a waste product, but the oceans were rich in dissolved iron. As oxygen entered the water, it reacted with iron to form rust, which settled to the seafloor in layers. The banding may reflect seasonal or other cyclical changes in oxygen production. These formations are our primary source of iron ore today, and they mark the transformation of Earth from an anoxic world to one where oxygen would eventually fill the atmosphere. There was once a time when the seas were purple. Before cyanobacteria dominated the oceans with their green photosynthesis, other microorganisms may have ruled the waters. Some scientists propose that early life used a purple pigment called retinal to harvest sunlight, rather than the green chlorophyll that dominates today. If this theory is correct, the ancient oceans would have appeared purple rather than blue-green. Evidence for this purple Earth hypothesis comes from the fact that retinal-based photosynthesis is simpler and may have evolved first. Chlorophyll absorbs red and blue light, reflecting green, perhaps an adaptation to avoid competition with earlier purple organisms. The idea of purple seas remains debated, but it reminds us how different early Earth may have looked. Oxygen in the air was first made by ancient microbial mats. The oxygen we breathe today is a biological product manufactured by photosynthetic organisms over billions of years. The first significant oxygen producers were cyanobacteria, forming microbial mats in ancient shallow seas. These organisms used sunlight to split water molecules, releasing oxygen as a waste product. At first, this oxygen was absorbed by reactions with iron and other elements in the environment. Only after these sinks were saturated did oxygen begin accumulating in the atmosphere, fundamentally transforming the planet. This great oxidation event, roughly 2.5 billion years ago, made possible the complex life that would eventually emerge. Every breath you take connects you to those ancient microbial pioneers. Coral reefs are living geological structures made of calcium skeletons. Coral reefs are biological constructions on a geological scale, built over thousands of years by countless tiny animals. Each coral polyp secretes a calcium carbonate skeleton, and as generations of polyps build upon their predecessors, massive reef structures form. The Great Barrier Reef stretches over 2,000 kilometers, visible from space, yet built by organisms just millimeters in size. Fossil reefs record ancient environments and the evolution of reef-building organisms through time. The oldest coral reefs appeared hundreds of millions of years ago, though modern reef systems date from more recent geological time. These living structures shape coastlines, protect shores from storms, and host a quarter of all marine species in their intricate calcium architecture. Earth once turned completely white during Snowball Earth. Between about 700 and 600 million years ago, Earth may have experienced the most extreme ice age in its history. During Snowball Earth, glaciers extended from the poles all the way to the equator, covering the entire planet in ice. Evidence for this frozen state comes from glacial deposits found at tropical latitudes, where ice should not have existed. The oceans would have been covered by ice perhaps a kilometer thick, with only occasional patches of open water. How life survived this frozen catastrophe remains a mystery, though volcanic hot springs and thin ice near the equator may have provided refuges. This frozen world lasted millions of years before something dramatic brought the thaw. Volcanoes may have ended that frozen age with a greenhouse burst. While Earth was locked in ice, volcanoes continued to erupt beneath the frozen surface. Normally, weathering of silicate rocks removes carbon dioxide from the atmosphere, but with everything frozen, this process stopped. Volcanic gases accumulated in the atmosphere for millions of years, with no mechanism to remove them. Eventually, greenhouse gas concentrations became so high that they triggered rapid warming. The transition from icehouse to hothouse may have been dramatic, with temperatures swinging from extreme cold to extreme heat in geologically brief periods. This volcanic escape from Snowball Earth may have triggered the explosion of complex life that followed as new nutrients flooded the oceans. Glaciers carve landscapes like moving rivers of rock. Glaciers are powerful agents of geological change, reshaping entire landscapes as they flow. Carrying rocks frozen into their base, glaciers grind the bedrock beneath them, carving U-shaped valleys with characteristic steep walls and flat floors. They pluck rocks from mountain peaks, creating jagged cirques and knife-edge ridges called arites. Rocks transported by glaciers are dumped in moraines when the ice melts, forming hills and ridges of debris. The fjords of Norway, the Great Lakes of North America, and the Matterhorn of the Alps all owe their shapes to glacial erosion. These slow-moving rivers of ice can transform landscapes more dramatically than any other geological force, except volcanism. Some glaciers move fast enough to be seen shifting by the hour. While most glaciers flow at rates measurable only in meters per year, some glaciers move remarkably fast. Jakobshavn Glacier in Greenland flows at speeds exceeding 40 meters per day, fast enough that movement can sometimes be observed over hours. These fast-moving glaciers are often outlets for vast ice sheets, funneling enormous quantities of ice toward the sea. Their speed depends on factors like basal temperature, water lubrication, and ice thickness. As climate changes, many glaciers are accelerating, dumping more ice into the oceans and contributing to sea level rise. The fastest glaciers are among the most dynamic and visually dramatic geological features on Earth, flowing like rivers in slow motion. Ice under pressure behaves like slow-flowing honey. Ice may seem like a brittle solid, but under the immense pressure of a glacier, it behaves more like an extremely viscous liquid. The weight of accumulated ice causes the lower layers to flow slowly outward, much like honey spreading on a surface. This plastic deformation allows glaciers to flow around obstacles and through mountain valleys. The ice crystals within a glacier slowly recrystallize under pressure, aligning in response to stress. This flow occurs even while the surface ice remains brittle and cracks into crevasses. The dual nature of glacial ice, brittle on top and flowing beneath, creates the dynamic, ever-changing landscape of ice that defines glaciated regions. The Moon stabilizes Earth's wobble, shaping long-term geology. Earth's axis wobbles like a spinning top, and without the Moon, this wobble would be chaotic and extreme. The Moon's gravitational influence stabilizes Earth's axial tilt, keeping it within a relatively narrow range over millions of years. This stability is crucial for maintaining consistent climate patterns that allow ice ages and warm periods to cycle predictably. Without the Moon, Earth's tilt could vary wildly, swinging from 0 to 90 degrees over geological time. Such extreme variations would cause dramatic climate shifts, with the poles alternately frozen and baking. The Moon, by steadying our planet's spin, has been a silent guardian of geological and biological stability throughout Earth's history. Earth's magnetic field has flipped hundreds of times throughout history. The magnetic north and south poles of our planet have switched places many times over geological history. During a reversal, the compass that now points north would instead point south. These flips occur at irregular intervals, sometimes separated by millions of years, sometimes by only a few 100,000. Evidence for past reversals is preserved in volcanic rocks and seafloor sediments, which record the magnetic field direction at the time they formed. The last major reversal occurred about 780,000 years ago. The causes of magnetic reversals are still not fully understood, but they arise from complex dynamics in Earth's liquid iron outer core, where convection currents generate the magnetic field. During those flips, compass needles would have pointed south. During a magnetic reversal, the polarity of Earth's magnetic field is effectively reversed. Compasses developed in those times would have pointed to geographic south rather than north. The transition between polarities is not instantaneous, but occurs over thousands of years, during which the field may weaken, wander, and even develop multiple poles. Some studies suggest that during reversals, the field strength drops to about 10% of normal levels. This weakened state might have consequences for life, allowing more cosmic radiation to reach the surface. However, there is no clear evidence linking magnetic reversals to mass extinctions, suggesting that life has adapted to these periodic upheavals. Even today, the magnetic poles wander by miles each year. Earth's magnetic poles are not fixed points but wander continuously. The North Magnetic Pole is currently moving from the Canadian Arctic towards Siberia at a rate of about 50 to 60 kilometers per year, faster than at any time in recorded history. This polar wander is driven by changes in the flow of liquid iron in the outer core. Throughout history, the poles have wandered across vast distances, sometimes far from the geographic poles. This wandering is independent of magnetic reversals and occurs even during periods of stable polarity. Navigation systems must constantly update their magnetic models to account for this restless shifting of the poles. Rocks become magnets after cooling from lava. When molten rock cools below a certain temperature called the Curie point, magnetic minerals within it align with Earth's magnetic field and become locked in place. This process, called thermormanent magnetization, turns the rock into a permanent record of the magnetic field at the time of its formation. Scientists can measure this fossil magnetism to determine the strength and direction of ancient magnetic fields. This technique, called paleomagnetism, has been crucial for understanding plate tectonics, proving continental drift, and mapping the history of magnetic reversals. Every volcanic rock is a time capsule, preserving a snapshot of Earth's invisible magnetic field from the moment it solidified. The magnetic field shields life from cosmic radiation. Earth's magnetic field extends far into space, creating a protective bubble called the magnetosphere. This invisible shield deflects the constant stream of charged particles flowing from the Sun, known as the solar wind. Without this protection, the solar wind would strip away the atmosphere over geological time, as happened to Mars after its magnetic field faded. The magnetosphere also protects life on the surface from harmful cosmic radiation. During magnetic reversals, when the field weakens, more radiation may reach the surface, though the atmosphere provides additional shielding. This magnetic armor has been protecting Earth and its life for billions of years, generated by the churning currents of molten iron deep in the core. Desert sand can sing with a low musical note when it moves. In certain deserts around the world, sand dunes produce mysterious sounds when disturbed. These singing sands, also called booming dunes, create low-frequency sounds that can be heard from kilometers away. The phenomenon occurs when dry sand grains of uniform size slide down a dune face, vibrating together like a natural instrument. The sound has been compared to the drone of an aeroplane, the hum of a bass guitar, or even the rumble of distant thunder. The exact mechanism is still debated, but it appears to involve the synchronized motion of billions of sand grains. Ancient travelers recorded these sounds with wonder and sometimes fear, attributing them to spirits of the desert. Some beaches are made entirely of tiny shells. Not all beaches are made of rock-derived sand. Some shores are composed almost entirely of shell fragments, the accumulated remains of countless marine organisms. Shell beaches form where shell-producing organisms thrive and wave action grinds their remains into sand-sized particles. Shell Beach in Western Australia stretches for over 100 kilometers, built from the shells of billions of tiny cockles. The shells accumulate because high salinity discourages the creatures that would normally consume them. Other beaches are made of coral fragments, sea urchin spines, or the skeletal remains of calcareous algae. Each grain on these beaches was once part of a living organism. There are black, green, pink, and even red sands on Earth. Beach sand comes in a surprising variety of colors, each reflecting the local geology and biology. Black sand beaches form from volcanic rock, where lava rich in iron and magnesium erodes into dark mineral grains. Green sand beaches, among the rarest on Earth, contain the mineral olivine, a green crystal found in basalt. Pink sand beaches owe their color to crushed coral and the shells of tiny pink organisms called foraminifera. Red sand beaches often contain iron-rich minerals or red coral fragments. White sand is typically quartz or calcium carbonate, while golden sand may contain feldspar. Every beach tells a geological story through its color. Tides caused by the moon sculpt coastlines across millennia. The moon's gravitational pull raises the ocean into tidal bulges that sweep around the planet twice daily. Over thousands of years, this constant rising and falling of the sea sculpts coastlines, carving cliffs, sorting sediments, and creating tidal flats. The intertidal zone, that strip of shore between high and low tide, is one of the most dynamic environments on Earth. Tidal currents transport sediment, feed estuaries, and shape barrier islands. The strength of tides varies with the moon's phase and orbit, creating spring tides and neap tides that affect coastal erosion differently. Every coastline on Earth bears the subtle signature of the moon's tireless influence. Dust from deserts can fertilize entire rainforests across oceans. Every year, hundreds of millions of tons of dust rise from deserts and cross entire oceans on prevailing winds. Saharan dust routinely travels across the Atlantic to fertilize the Amazon rainforest, delivering phosphorus and other nutrients that are scarce in the ancient, weathered soils of the Amazon basin. This transcontinental nutrient transfer has been measured by satellites and traced through chemical analysis. Without this desert dust, the Amazon might be far less productive. Dust from Asian deserts fertilizes the Pacific Ocean and even reaches North America. These aerial rivers of minerals connect distant ecosystems in ways we are only beginning to understand. Some coral reefs are older than many mountain ranges. While individual coral colonies may live only decades or centuries, coral reef structures can persist for millions of years. The fossil record shows that reef building has been occurring for over 500 million years, with modern reef systems dating back tens of thousands of years. The Great Barrier Reef began forming about 20,000 years ago, as sea levels rose after the last ice age, building on much older foundations. These biological structures have survived mass extinctions, sea level changes, and climate shifts. The Himalayas began rising about 50 million years ago, making many coral reef systems actually older than some of Earth's most impressive mountain ranges. Meteorites on Earth tell stories from before our planet was born. Every meteorite that falls to Earth is a messenger from the early solar system. Most meteorites are fragments of asteroids that formed within the first few million years of the solar system's existence, preserving conditions from before Earth even existed. Some contain mineral grains that predate the Sun, actual stardust from earlier stellar generations. By studying meteorites, scientists can learn about the composition of the solar nebula, the processes that built the planets, and the conditions in which life's precursor molecules might have formed. Each meteorite is a time capsule from an era when our solar system was a swirling disk of gas and dust around a young star. Some rocks are older than the solar system itself. Within certain meteorites are tiny grains called pre-solar grains that formed in the atmospheres of dying stars before our solar system existed. These microscopic particles survived the formation of the Sun and planets, preserving their stellar origin. Analysis of these grains reveals that they came from red giant stars, supernovae, and other stellar environments. The oldest pre-solar grains discovered so far are approximately 7 billion years old, predating our solar system by more than 2 billion years. These ancient stardust particles are among the oldest solid matter we can study directly, offering windows into stellar processes that occurred long before Earth formed. Lunar rocks brought back by astronauts help date Earth's early crust. The Moon preserves a record of early solar system history that Earth has lost through plate tectonics and erosion. Lunar samples returned by Apollo astronauts have been crucial for understanding the formation and early evolution of both worlds. Dating of lunar rocks helped establish the timing of the Late Heavy Bombardment, a period of intense asteroid impacts about 4 billion years ago. By comparing lunar and terrestrial samples, scientists can reconstruct the conditions on early Earth, when both bodies were subjected to similar bombardment. The Moon serves as a geological time capsule, preserving evidence that has long since been erased from Earth's surface. The oldest minerals ever found are tiny zircons from ancient Australia. In the Jack Hills of Western Australia, scientists have found zircon crystals that are nearly 4.5 billion years old, the oldest known terrestrial materials. These tiny crystals, each no larger than a grain of sand, survived the destruction of the rocks that originally contained them and were transported into younger sediments. Their extreme durability preserved them through eons of geological upheaval. Analysis of these ancient zircons has revolutionized our understanding of early Earth, suggesting that conditions were cooler and more hospitable than previously thought. These microscopic time travelers carry information from an era almost inconceivably distant. These zircons record the first liquid water on Earth. The ancient Jack Hills zircons contain oxygen isotope ratios that suggest they formed in the presence of liquid water. This discovery pushed back the evidence for surface water on Earth by hundreds of millions of years. If liquid water existed 4.4 billion years ago, the early Earth was not the hellish molten world often imagined. It may have had oceans, rainfall, and conditions conducive to the origin of life far earlier than previously thought. These zircons, smaller than a hair's width, carry evidence that water, the essential ingredient for life as we know it, was present almost from the beginning. Rocks on Earth contain tiny fragments of stardust. Beyond meteorites, even ordinary rocks on Earth can contain microscopic grains of interstellar origin. During the formation of the solar system, some pre-solar material was incorporated into the growing Earth. Additionally, interplanetary dust particles, some of which originate from comets and asteroids, continuously rain down on Earth. Scientists have extracted pre-solar grains from Antarctic micrometeorites and even from deep-sea sediments. These particles carry isotopic signatures that identify their stellar origins, whether from supernova explosions, red giants, or asymptotic giant branch stars. The ground we walk on contains the literal ashes of stars that died before our sun was born. Even today, space dust adds hundreds of tons of new material each day. Earth is not a closed system but constantly receives material from space. Every day, approximately 100 to 300 tons of cosmic dust drifts down through the atmosphere, adding to Earth's mass. Most of this material is too fine to notice, settling invisibly across the planet's surface. Larger particles may briefly glow as shooting stars before their remnants reach the ground. Over billions of years, this cosmic rain has added substantial material to Earth, including water from icy comets and organic molecules that may have seeded the origin of life. The planet is still growing, grain by grain, as it has been since its formation. Earth's surface is dotted with hidden scars from ancient collisions. Impact craters pepper Earth's surface, though many are hidden or eroded beyond recognition. Geologists have identified nearly 200 confirmed impact structures, from tiny bowls to massive scars hundreds of kilometers across. Many more likely remain undiscovered, buried beneath sediments, hidden underwater, or erased by plate tectonics. The circular structures of craters may reveal themselves through unusual rock formations, shatter cones, or the presence of shocked minerals that form only under impact pressures. Each crater represents a catastrophic moment in Earth's history when a projectile from space struck our planet, reshaping landscapes and sometimes changing the course of evolution. One giant impact may have triggered the age of the dinosaurs. About 201 million years ago, at the end of the Triassic period, a mass extinction wiped out many of the dominant land animals, clearing ecological niches for dinosaurs to fill. The cause of this extinction is debated, but some evidence points to a large asteroid impact. The Manicouagan crater in Quebec, one of the largest visible impact structures on Earth, formed around this time. Whether this impact directly caused the extinction or contributed to other environmental stresses remains uncertain. What is clear is that in the aftermath, dinosaurs rose to dominance, beginning a reign that would last over 130 million years. Another impact ended it 66 million years ago. The asteroid that struck the Yucatan Peninsula 66 million years ago delivered one of the most devastating blows in Earth's history. The impact released energy equivalent to roughly 10 billion tons of TNT, igniting global wildfires, triggering earthquakes and tsunamis, and blasting so much debris into the atmosphere that sunlight was blocked for years. Photosynthesis collapsed, food chains broke down, and temperatures plummeted. This impact winter killed the non-avian dinosaurs and about 75% of all species on Earth. Only small animals, those that could burrow or survive on detritus, made it through. From the ashes of this catastrophe, mammals would eventually rise to dominance. Some impact craters are so eroded, they are almost invisible. Earth's oldest impact craters have been subjected to billions of years of erosion, burial, and tectonic deformation. Identifying these ancient scars requires careful geological detective work. Some craters appear only as circular patterns in vegetation or drainage, visible best from aerial or satellite imagery. Others are detected through anomalies in gravity or magnetic measurements. The Vredefort crater in South Africa, formed over 2 billion years ago, has been so deeply eroded that only its root structure remains, a subtle circular feature that once hosted one of the largest impacts in Earth's history. These invisible scars remind us that Earth's violent past is often hidden. The Chicxulub crater remains buried beneath layers of limestone. The impact structure that ended the age of dinosaurs lies beneath the northern Yucatan Peninsula, buried under hundreds of meters of limestone, deposited in the millions of years since the impact. The crater, about 180 kilometers in diameter, was discovered through gravitational anomalies and confirmed by drilling. Its ring of sinkholes, called cenotes, marks the crater's outer edge, where fractured rock allows groundwater to flow. The buried crater preserves evidence of the catastrophic event, including shocked quartz, melted rock, and layers of debris that spread across the globe. This hidden scar shaped the course of life on Earth. Impact events have repeatedly reset the course of evolution. Mass extinctions caused by asteroid impacts have fundamentally altered the trajectory of life on Earth. By wiping out dominant groups of organisms, these catastrophes create opportunities for survivors to diversify and fill vacated ecological roles. The end Cretaceous impact allowed mammals to rise from small, marginal creatures to dominant megafauna. Earlier impacts may have contributed to other extinction events throughout Earth's history. Without these cosmic interventions, the history of life would have unfolded very differently. Humans might never have evolved if dinosaurs had continued their reign. Impact events, while devastating in the short term, have been engines of evolutionary change. More than 70% of species vanished after the Chicxulub impact. The extinction event that followed the Chicxulub impact was one of the most severe in Earth's history. All non-avian dinosaurs disappeared, along with pterosaurs, marine reptiles, ammonites, and countless other groups. On land and in the sea, ecosystems collapsed as food chains were disrupted. Recovery took millions of years, as surviving species slowly diversified to fill empty niches. The selectivity of extinction was striking, with some groups devastated while others survived relatively unscathed. Birds, the living descendants of dinosaurs, made it through, as did crocodilians, small mammals, and many insects. The survivors inherited a transformed world, beginning anew in the shadow of catastrophe. And so, our gentle journey through the wonders of geology draws to a close. We have drifted through billions of years of planetary history. We have wandered among crystals in hidden caves and marveled at forces that split continents and raise mountains from the sea. We have followed the story of the Earth as it stretched and shifted, erupted and eroded, again and again across unimaginable spans of time. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the slow pulse of the planet itself, like the patient grinding of stone against stone. The Earth has survived asteroid impacts, ice ages, and the wandering of continents. It has transformed endlessly, yet endured. And you are part of it all. The atoms in your body were forged in dying stars, and carried here by ancient meteorites. The ground beneath you has traveled across the globe, carrying the memory of vanished oceans and forgotten mountains. You do not need to hold on to any of these facts. Just let them drift. Let them settle like sediment in a quiet sea. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that you rest upon a living planet, one that has been breathing and changing for 4.5 billion years. Thank you for joining me on this journey through the geology of Earth. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of the natural world. There are more wonders waiting, more mysteries hidden in stone, more secrets to drift through on quiet evenings. Rest well, and may the stillness of the earth keep you company through the night. This has been Drowsy Discovery. Good night.